Hello, welcome to a new chapter of Theoretical Mechanics course. Today we're going to do exercise 2, and this exercise consists of a complex Klein-Gordon field, and we will not do the first section because I already did it in the previous chapter, so we'll start with section B that says determine the conjugate momenta and the Hamiltonian density. Okay, remember the definition of pi, the conjugate momenta or momentum of x, is the partial derivative of the Lagrangian density with respect to partial 0 phi. So in order to compute this, notice that the dependency on partial derivative is only in this first term. So let me calculate the partial, in general, the partial derivative with respect to partial alpha phi of partial mu phi star, partial nu phi. This term can go outside, partial mu phi star times the partial derivative, and we can lower this index by putting g mu nu partial nu phi. So the metric can come out of this parenthesis. Let's put g mu nu here times partial mu phi star. And then we have the partial derivative of partial nu phi with respect to partial alpha phi. This gives us Kroneker's delta nu alpha. This contraction gives us partial nu phi star, and the contraction of this term with this term gives us partial alpha. So this is the result, the final result. We are asked to find in the particular case that alpha is 0. So this is the end of the calculation. And again, if you conjugate the whole equation, you will obtain p star of x equals the conjugate of this term. So we will have partial 0 phi, because again, the Lagrangian density is a real magnitude. So that's it. Okay, let's calculate the Hamiltonian density. The Hamiltonian density is defined by means of pi partial 0 phi plus pi star partial 0 phi star minus the Lagrangian density. But remember, the metric signature is 1 minus 1 minus 1 minus 1. So this 1 allows us to raise this index and this index without changing the sign. And then we see that this is pi star and this is pi. So let's substitute, and we can put this term twice because it's the same that this term. And now let's substitute the Lagrangian density. It will be partial 0 phi star, partial 0 phi plus partial I phi star, partial I phi minus m squared phi star phi minus lambda over 4 phi star phi squared. Okay, let's raise this index again, and we see this is pi and this is pi star. So 2 pi pi star minus pi pi star is 1 pi star. And let's change the sign. This is minus plus plus, and we can delete this minus, and this is the final result. We can do something else, because we can lower the index changing the sign, minus partial I phi. This minus with this minus is plus. And remember, this is a sum, and then it's convenient to write the sum from I equals 1 to 3. This summation is needed because if you want to perform a summation, the Einstein's criterion says that you must have a downstairs index and upstairs index. So if you have here two indices upstairs, you need to put a summation. Now this is the definition of the scalar product of gradient phi star, gradient phi. This is the definition. Dot product, the Euclidean dot product. Remember, this is a complex number, and also this, so we can also write this thing in this way, and also this thing, of course. So another way to put this is pi of x with the bars square plus the gradient of phi square plus m square phi star phi plus lambda over 4. And if you want, we can do the same thing here, phi modulus square plus lambda over 4 modulus to the power of 4. So, okay, that's it. Let's write it down here. By the way, this is B. Let's do section C, calculate the stress energy tensor, or also called energy momentum tensor. And remember the definition. G mu nu equals the sum over A is some index, partial L with respect partial mu phi A, partial nu phi A, minus G mu nu L. But what is the meaning of this index? In this case, we can call phi 1 to phi and phi 2 to phi star. Putting this index here allows us to different independent component. This is the reason because I put this here, because if I don't put this here, you can think that there is only one term, and there are two terms because there are two things that are independent. So if you want, we can repeat the term, this term, delete this thing, delete A here, and delete this A and this A, but putting a star here and summing. Now is the thing. So remember, in section A, we've calculated this thing. In fact, this thing is partial mu phi star, if you remember, a few minutes ago. And this term is partial mu phi. So that's it. So let's put these two things here. And now let's substitute L. It will give us partial mu phi star partial mu. Let's change this mu by another index, alpha, for instance, so we don't get confused with this mu and this nu. Okay, minus m square phi star phi minus lambda over 4 phi star phi square. So let's compute T00. T00 will be partial 0 phi star partial 0 phi plus partial 0 phi partial 0 phi star minus G and 0, that is 1, minus partial alpha phi star partial alpha phi minus m square, all these things. So let's change the sign, minus and plus, and if we lower the index, this index and this index, because of this reason, the same reason as before, if we subtract this minus this, the survival term is minus partial I phi star partial I phi. So let's delete this and let's substitute this without the minus, because this minus is this minus. So we can raise this index again without changing anything, and this is pi star, this is pi, and if we lower this index I, we now have to change this sign and put a sum here. So this is again the gradient of phi star, that product, the gradient of phi. So again we recover this term and this term and these terms. So we have the Hamiltonian density as we expected. Let's calculate G0I. This will give us partial 0 phi star partial I phi plus partial 0 phi partial I phi star and 0, because G is diagonal and G0I is 0. So this is pi if we lower the index, this is minus partial I phi, and looking at this is pi star. And if we lower this index, we put a minus sign here, partial I phi star. So minus pi star partial I phi star. So let's write it down. G0I equals minus pi partial I. If you want, let's write the index again, because it's nicer if we put the I index upstairs. In the left-hand side of the equation, the index I is upstairs. Phi plus phi star partial I phi star. Okay, so let's now compute I0 instead of 0i. Then also this is 0. Instead of putting 0i, 0i, we will have I0, I0. But again, this is pi star, this is pi, and this is the same thing as before, as G0i. This is a general property of the stress energy tensor. And finally, we can compute Tii, and let's see. Tii is partial I phi star, partial I phi, and this is the same, so we can put here 2 minus Gii, but Gii is minus 1, with this minus is plus, so we can sum and we can write the same thing. But notice that this is not a sum. This is important, etc. But the general calculation of complex Klein-Gordon field is this result. Check that L is invariant under the phase transformation phi going to exponential of e to the I alpha phi. And notice in this exercise, alpha doesn't depend on x. If that was the case, then it will lead us to gauge transformation. But this is not the case. Alpha doesn't depend on x. So let me delete this so you can get confused. This is very easy, because if you have this and you perform this transformation, then what you get is e to the I alpha phi. But this is a constant that can come out from here, and then we obtain e to the I alpha partial mu. So the partial derivative of this thing is this exponential times this term. Okay, if this is true, this is also true with the index upstairs. This is a tensor property, but if this is true, this must be true also. So from this we will have partial mu e to the minus alpha phi star equals e to the minus I alpha partial mu phi star. So combining these two equations, we have that this term times this term is the same as this term times this term. These exponentials cancels out each other, so we finally have the same thing. So the kinetic term is invariant under this transformation, and the other terms are even easier, because e to the I alpha phi star times e to the I alpha phi. By the way, I'm looking here. This gives us e to the minus alpha phi star, e to the I alpha phi. These exponentials cancels out each other, so we obtain what we had before. And the same thing happens here, because the only difference between these two terms is this square, but this causes no effect. So yes, L is invariant under the phase transformation, this one. So if we have a continuous symmetry, or we say this is a continuous symmetry because alpha is a real number, a continuous number, this is the thing we need to apply Nether's theorem. So remember, Nether's theorem says that the conserved current is the sum over A partial L with respect to partial mu phi A times the variation of the field A minus the stress energy tensor mu alpha contracted with the variation of the coordinates, but this transformation has nothing to do with variations on x, on the positions. So the variation in this case is 0, so this term vanishes. The only thing we have left is this thing, and remember, this thing is the same as putting as a plus here, deleting A from here and putting and star for the same reasons we saw a few minutes ago. And remember, this is partial mu phi star and this is partial mu phi. So there it is, delta phi plus delta phi star. Okay, so the only thing we have left is to calculate this variation. Let's calculate this variation. If phi prime of x is e to the I alpha phi x, then the variation of phi due to a transformation into the external space of the field, not in the position, is defined as phi of x minus phi of x. But you have to consider alpha as infinitesimal number. So if this is the case, then we have the first term of the Taylor expansion, namely 1 plus I alpha times phi of x minus phi of x, and this 1 and this field with minus this field, these terms cancel out, so the remaining term is I alpha phi of x. So if we have this, then automatically have this, because we can perform the conjugation of this equation and we will have minus I alpha phi star of x. And the only thing we have to do is to substitute, and that's it. Minus alpha, alpha is a real constant, so there's no star here in both alphas. So if we factor out I alpha, we have partial mu phi star, and delta phi is I alpha times phi of x minus partial mu phi delta phi star, and this is phi star. So in order to avoid confusions, let me change the order here. I think it's better because then you know that this partial derivative acts on phi star. And here we can do the same thing. By the way, the constants that multiply here, we throw them because are irrelevant. The important thing is that this combination of objects is what remains constant. The last thing we have to do is check it is conserved. Okay, let's do it. The conservation of the current means if we take the derivative, partial mu derivative of the current, this must be 0, identically. So let's perform this derivative. Let's put this derivative in yellow. So let's see. Partial mu phi partial mu phi star minus phi star partial mu phi is partial mu phi star plus phi partial mu phi star. This is the derivative of the first term minus partial mu phi star partial mu phi minus phi star partial mu phi. If you remember, the equations of motion tells us that this is the same as minus m squared phi star minus lambda over 2 phi star square phi. And the equations of motion for this field tells us minus m squared phi minus lambda over 2 phi squared phi star. So if we multiply this term by phi and this term by phi star, we see that this times this is the same that this times this, and times this is also the same as this times this. So here we have a plus, a minus, so this term cancels with this term on shell. This is an important thing because when we say that this is conserved, we mean on shell, namely when the equations of motion are fulfilled. So this term vanishes with this term, and using the property that states that this Lorentz dot product is the same as mu extending upstairs and mu downstairs, we see that this thing is the same as this thing, and this thing the same as this thing, and this is with this minus, this gives us 0. So remember, the conservation of the current fulfill if we are on shell. This is an important issue. So I think we're done. Goodbye.